which you guys uses in the uh, numerical. So what is this first formula? The first formula, heat rejected at condenser QC is equals to H2 minus H3. You know that process 1 to 2 takes place in compressor, process 2 to 3 takes place in condenser, process 3 to 4 it is isenthalpic process take place at expansion wall, and process 4 to 1 is evaporation and takes place in evaporator. So guys, some information is written here also that HF3 is equals to HF4 plus X4 into HFG of 4, where X4 is dryness fraction. This Hg4 is enthalpy of evaporation. Enthalpy of evaporation, enthalpy of liquid, enthalpy of liquid at condenser, enthalpy of saturation is I already show you how they are going to give this data in the numerical and how we are going to use. Then this is for refrigerating effect, which is H1 minus H4. Then COP, formula of COP is H1 minus H4 upon H2 minus H1. Similarly COP actual, it is plant capacity upon compressor work. We are going to use this formula in numericals. So here are your numericals. Before this, again, these are the types of formula that how we are going to calculate the enthalpy at various point or enthalpy at exit of the compressor. So this is H1 is equals to HF1, enthalpy of liquid plus dryness fraction is equal to the enthalpy of evaporation. We are using this formula when wet compression is occurs, or when the refrigerant entering the compressor is not dry and saturated. Similarly, this is type 2. If at entry of compressor the refrigerant is dry and saturated, at this time H1 is equals to H of G, and H2 is equals to Hg2 plus HF2 plus HFG2 plus Cp into T2 minus T2 dash. The description of this is already I show you in this page also, you can read this. And similarly, next type, when refrigerant is superheated, for subcooling, when no subcooling performs, you have to use this condition in the numerical. This page is very much important. So this is the numericals, my child, which is the simple one. I take this numerical in the class also and in our extra lecture also, when some students come to me for this extra lectures. A VCR refrigerant work on between 4.98 and 1.86 bar. The temperature of, also this is the pressure at which the compressor and condenser are working, which is 4.98 and 1.86. Here again the information is stated that the liquid is subcooled to 9 degree, dry before compression. Means what? It is wet compression takes place. Dryness fraction is given as x is equals to 0.95. Okay. You can see here the point 1 is taken in the wet region. If they are telling that this refrigerant entering the compressor is dry and saturated, at that point we will take this point 1 on the saturation curve. But they are telling that our vapor is 95% dry, means it is 5% wet. So we are taking this point 1 in the wet region and start compressor like this. Okay. And also they are telling that the compressor there is subcooling is present. So how we understand that there is a subcooling is present? You can see that the numerical they are stating that the liquid is subcooled to 9 degree before throttling. Means what? Before throttling the subcooling is provided, which is 3-3. Now you can see that we are using this formula of H1 is equals to F HF1 plus Hx into HFG1. How we use this formula is explained in the previous page, that the conditions which I wrote there, just learn through it. And we are using this formula of H2, which you will get on that page. We are putting the value of there and calculate the formula. Similarly, we are using here the formula for COP, which is H1 minus H4. Putting the values, and we are getting the COP as 4.5. Now in examination the COP should be less than in the range of 4 to 8 should be less than 8. If your COP is coming as 50, 60, then consider then check your numerical again, and you will find something, because many standard COP of vapor compression refrigeration cycle is comes below 8. Similarly, we are taking this another numerical. Here what happens, here is again wet compression, and the vapor leaving the compressor as are dry and saturated, and here no subcooling is provided. So formula will be something changing there. Let's just try to use proper formula. Here again they are not providing us the dryness factor. Here they are not providing us the dryness factor. For this you need to find this dryness fraction. For this we are using this entropy. They are provided here S1 S2. Then we are finding this S1 S2, then comparing S1 S2 to finding the dryness fraction. Then this dryness fraction should become below the 100 below 1. The dryness fraction should be 0.7 to 0.99. In that region your dryness fraction should be come. Then putting the value of dryness fraction in H1 H2 formula, and we are getting this value here. This is the third numerical which I took in your in class. Here what happens, here is the weight compression. Here is the weight compression performed along with the superheating, and no subcooling is provided here. This numerical is quite simple. Here just whenever there is the weight compression is provided, at this time you need to calculate the X dryness fraction. Sometimes X may be given in the examination. So dryness fraction is already given here, which is 0.96. So but here we are not having the value of that CPV. So to finding CPV we are equating this S1 is equals to S2, and then finding value of CPV, then finding the value of H2, value of H1 by here we are calculated the value of H1. Calculate the value of H2, we need the value of CPV. So after knowing the value of CPV we are getting value of H2. Then here we are using the formula COP is equals to H1 minus H4 of H2 minus H1. By putting the value we are getting value as 4.97. I already told you that the value of COP should be less than 8. Same here is the rise in temperature they are asking. This formula is also easy one, not much more hard. Then these are the